Hello, good morning or good afternoon, everybody. Welcome into this fourth session of the Molecular Evolution and Phylogenetics module. Today we're going to talk about heuristics for tree inference based on three alterations. We're going to talk about the maximum likelihood framework, the Bayesian methods, and statistical confidence measures on the branches on a tree once it's built. Learning objectives are listed on this slide. No basic tree rearrangements widely used in the literature and in inference programs. Know about the likelihood of a tree and maximum likelihood methods, Bayesian methods, and bootstrap procedures. Learning outcomes are here. You'll be able to run maximum likelihood analysis. You'll be able to understand, of course, how it works. Understand the basic parameters of Bayesian inference methods, and to be able to interpret the supports on branches that are output by phylogenetic inference programs. So, we're going to start with reviewing a few strategies to find the best phylogenetic tree, or one of the best phylogenetic trees, and we're going to see how to browse the space of topologies. So remember that the tree inference problem is an optimization problem. We're going to find a tree that maximizes or minimizes a certain criterion, and you have this criterion set beforehand. For instance, in the parsimony, maximum parsimony methods, we want to find a tree that minimizes the cost in terms of steps or evolutionary events of substitutions that take place on the branches, parsimony cost. And also remember that we have a huge number of possible binary tree topologies when we have n taxa on the leaves of this phylogeny. So the double factorial of 2n minus 5, remember it's 3 times 5 times 7 times 11, etc., times 2n minus 5. So I gave you a few figures during the last session, but you understand that this number grows exponentially very fast, and so it's not possible in any case to explore and to test all possible tree topologies. Okay, when you are given aligned sequences on a certain set of taxa, it is not possible to explore all the tree topologies on this set of taxa. So we have to devise some method to explore as efficiently as possible the space of possible topologies, just picking some of the possible topologies in order to try and find the best tree. So we need to guide the search with a certain criterion or set of criteria, and we need to develop heuristics to decide which tree to try next. Once we have tried a tree, which is the one to try next, and when do we stop in our quest for the best tree? Okay. So we have to optimize a certain criterion. We try optimize it, and at some point, maybe when we cannot find a better tree, then we will have to stop the search. So when we say heuristics, it's basically methods that are not guaranteeing you to get the optimum. Okay, heuristics means like recipes that try their best, but are not guaranteed to give the maximum. So, what phylogenetic inference software do, and remember, phylogenetic inference means infer, calculate the tree given a certain number of data on the leaves. So these inference software implements pseudo-random walks in the space of tree topologies. Imagine that the space is big. Every point in this space is a tree topology or a phylogeny without branch length, because optimization of the branch length is something a bit different, something else. So software try and browse the space of all possible topologies, and they perform what we call a random walk or pseudo-random walk, jumping from one topology to another and trying to see if the criterion that is in use is minimized during this random walk. Okay, so you perform this walk while trying to reach regions of the space of all phylogenies where your criterion tends to become minimum. And we'll go from one tree to the next with elementary tree alterations, and we're going to review these three alterations in the next slides. They are called NNI, SPR, and TBR moves. And it's an iterative trial and error process. I describe here the general framework with which phylogenetic inference programs work. So they try one tree, they calculate the corresponding parsimony cost. That's in case where the parsimony is the framework in which we're working. Otherwise, they would try and calculate the likelihood of the tree, but we've not introduced likelihood yet. So calculate the corresponding parsimony cost, and because it's your objective to minimize it, then try improve this parsimony cost. In other terms, try to reduce this parsimony cost with a slight modification of the tree. Okay. And for instance, while you're trying to find the best elementary tree alteration, you'll try to pick the move leading to the largest improvement or the largest decrease in terms of parsimony cost. And then you calculate the new cost. So you are sitting on a new point in this space of all possible topologies. And from this, you will try to improve again, etc., etc. So that's this random walk. It's not completely random because you don't go at random. You go through this space having a criterion that you try to optimize, and so this criterion leads your search. So try random alterations. Sometimes we'll see that it's necessary to conserve this change. Sometimes we jumped from one point in the space of topology to another point, and we didn't improve on our criterion, so maybe we go back. Okay, we do some backtracking before attempting another alteration. So that's the generic framework, and we're going to see now the different elementary tree alterations that are routinely performed by the phylogenetic inference softwares. The first one is the simplest. Once you have so it's called nearest neighbor interchange, and it's a local rearrangement, right? So parts of the tree are not going to be modified. This is a local rearrangement, swapping two of the four subtrees connected to a given branch. So here, imagine I have this branch. It's always possible to represent in a tree locally. It's always possible to represent the tree as a set of four subtrees. Some of these four subtrees may be reduced to one leaf, okay? But these four subtrees around an internal branch, okay? Obviously, this is an internal branch. If it was an external branch, it would mean it's leading to a leaf, and then you would not have two subtrees. For instance, here you would just have one leaf here, okay? So we're talking about, here I should have said, of the four subtrees connected to a given internal branch. I'm going to modify this slide. So we're going to take two of these and swap them, and we'll obtain a new tree from the previous tree. Obviously, we cannot just swap T with U or swap R with S, because I remember from the last session, or from the previous one, I don't remember exactly, that if you just swap T with U, you're left with the same topology as you're having now. Okay, swapping R and S also gives you the same topology. It's not a different topology, it's the same. But now if you swap R with T, R with U, or T with S or T with R, which comes to the same, you have different topologies. Okay, so from this one you have two possible NNI moves, swapping T with S or swapping T with R. Okay, so here T with S is the same as having the closest neighbor of R becoming T. Okay, if you swap these two, T with S, the closest neighbor of R is T, and that's this one. Otherwise, you can swap U with S, and the closest neighbor of R becomes U, and that's what we have here. Okay, so we say that the distance between this tree and this tree, or the distance between this original tree and that other tree, is the distance of one NNI move, right? Because we just performed one NNI move to move from one to the other. So, why is it interesting, these moves? Why are these interesting? Because we'll see that lots of properties on the tree, like parsimony costs, like likelihood, can be computed on a subtree. So for instance, here, your parsimony cost linked to the subtree R, it's calculated one and for all, and then you will be able to calculate the new parsimony cost for this tree without having to recalculate the parsimony costs inside the subtree R, and we'll make use of this kind of information. So the algorithms propagate information from the subtrees to the rest of the tree. So NNI moves are the first example of elementary move from one phylogeny to another, from one topology to another. Let's have a short break here.